everyone, and welcome back again in Ask IITians Learning. So, we were having this discussion about periodic classification of elements, right? And in the past few classes, we have discovered and we have discussed a lot about what were the varied ways of classification, what was the need of classification, and the different attempts which have been made by Newland, Mendeleev's, Dobiner, and finally, in our last segment, like the last class, we reached to the modern periodic table. And we discovered that how Moseley, just by changing one word of atomic mass to atomic number, did a great discovery, right? Which has been still used nowadays. So we discussed a lot about his periodic table, that what are the specifications of his periodic table, the different names of each and every group. We discussed about icosahexagens, tetrahedrons, chalcogens, etc. Then we discussed short tricks, mnemonics to remember each group. Remember? And then we had a small discussion about that if you talk about the entire periodic table, it can be categorized into metals, non-metals, and metalloids, where again we discussed a trick to remember that. Then again, we discussed a trick to remember the metalloids, the number of metalloids and their names, right, which were forming a staircase-like structure. So that was all that we covered in our last class. In today's class, we'll be working more towards the trends which are there in the periodic table. Now, what do you understand by the term trends? See, now, the entire reason to create this sort of periodic table was to ease out the work, right? The only purpose was to ease out the work so that we can have the things present in a more organized fashion. Okay. So for that, we'll talk about the trends, like in the varied properties, how by looking at the trend, we can identify or we can use multiple elements for our benefit. So the varied trends which are present in the modern periodic table are valency, atomic and ionic size, metallic and non-metallic properties. These are the topics which are not the complete topics, but the topics which we are going to discuss in today's lecture. So without wasting time, let's proceed ahead in that direction. Now, this image that appears in front of you is a very vague image about periodic table, as we have already discussed in the last class. So we have a better table looking forward for you. All right, so these are the varied trends which are present in the modern periodic table, as you can see. Ionization energy, some heavy words. Electronegativity, the words you have never heard. Metallic character, non-metallic character still is bearable, easy to understand. Atomic radius, again, at least something which you can relate, right? So these are the ways in which the trends work. So as you can see here, this line represents, or if you have an arrow which is proceeding in the forward direction, it means the ionization energy value is increasing as you move from left to right. Ionization energy trends increases along the period. Same way, if you see the atomic radius. So as per the arrow part, they are trying to say that it increases down the group. So arrowhead is basically pointing the increasing direction, and whatever is written on the arrow, that is the property which is increasing in that direction, right? Now, why the property is increasing or decreasing in a particular direction? What do you understand by the term or that property's name? That all part we will be covering in this particular lecture. And as you already know, this part is quite important for your latter classes. So just sway, just feel the chapter as a normal chapter, nothing to pressure up. pressure you. Like, I have not given those details in the last class just to pressurize you. Just given you I've just quoted the fact so that you'll understand the importance of this chapter. Okay, so just with the eased state of mind, let's start working in the direction. And this chapter is really very easy. Trust me on this. All right, so the first property that we are going to cover in today's lecture is about the valency. Now, you all know about valency. You already are aware. Now, valency is what? It is the combining capacity of an element. The combining capacity of an element. Now, what do you mean by the term combining capacity? Okay, so it means the number of electrons lost, gained. The number of electrons lost or gained or shared during bond formation. Combining capacity is basically the number of electrons lost or gained or shared during the bond formation. This is something you've already done in your 9th grade, right? So, how does that change? So, the valency can be easily calculated from the electronic configuration. It can be easily calculated with the help of the electronic configuration. Now, how? So you know that, or you have certainly did this in your 9th grade, that valency is basically the number of valence electrons. This is, valency is equal to the number of valence electrons if the valence electrons are 1, 2, 4. So either if the valence electron is 1, the valency of that element will also be 1. If in the electronic configuration, if the outermost electrons or the valence electrons are 2, for instance, in calcium, so then the valency of calcium will also be 2, and so on. Now, the valency will be 8 minus the valence electrons if the number of electrons are higher or greater than 4. So if the number of electrons or the valence electrons are 5, 6, 7, or 8, in that case, you'll take the valency as 8 minus the valence electrons, right? And the reason was simple, which you've done last year, because every atom wants to complete its octet, okay? Or duplet. So basically, duplet means 2 electrons in the outermost shell, octet means 8 electrons in the outermost shell. So basic thing is that every element wants to attain noble gas-like configuration. Every element wants to attain noble gas-like configuration. Every element, right? So noble gases are the ones which are having complete outermost shell or complete valence shell. Now, in order to get that, either the outermost electrons needs to be lost. For instance, if I talk about sodium, right? So if I'll take this as the nucleus, so there are 2 electrons in the first shell, then 8 electrons in the second, and then in this third shell, there is 1 electron. Now, if you want to have an complete outermost shell, so there are 2 ways, right? One way is if I'll remove 1 electron. So in case I'll remove 1 electron, this entire shell is lost, right? Now, if the shell is lost, then what we are left with is only 2 shells. right? Either that way, or I should, gain 7 electrons. Now, gaining 7 electrons is actually a difficult task. Why is it difficult? That's because if you gain one more electron, right? The moment you gain one electron, then sodium will get a negative charge. Now, to that negatively charged atom, you are giving one more electron. Then to that two negatively charged element, you are giving one more electron. And you keep on giving that. So you know that like charges repel each other. You know that like charges repel each other. See, if you have to go along with someone who you do not like, so yes, you can bear that person for some time, like probably few minutes. Okay. But then if you have to wait, like if you are waiting someone or someone on the, let's say, on the roadside, so it's easy to wait for like a few minutes or like 10 minutes, 15 minutes, 20 minutes, right? But if that person is taking 3 hours, 10 hours to come, don't you think it will become tedious? So the same thing happens. If it has to like gain 1 or 2 electrons, it's all right. But when it has to gain 7 electrons, that's a big task. Okay. So as a result, this is simply unacceptable by that atom. So it simply thinks of losing 1 electron and having a complete octet, right? So this is the reason how the things work, or this is the way how the things work, right? Now, when you talk about any group, right? So in a group, your valency remains the same. In a group, valency remains same. Why? That's because electronic configuration remains similar. You have a similar electronic configuration. You have the same number of valence electrons, right? That's because in a group, it remains the same. For instance, let's see an example. So your example could be lithium, sodium, and potassium. Something you have done already. So you know that lithium's electronic configuration is 2,1, sodium is 281, and potassium is 2881. Now they all belong to the same group, that is group 1 elements, right? They all are group 1 elements. Now, their valence electron is 1, so that means their valency will also be 1, right? So they all have the same valency. So all elements which are lying in the same group will always have the same valency. Okay. So for group 1 and 2, their group number is equal to their valency. In cases of group 1 and 2, the group number also denotes the valency. Okay. Now see, here they have written group 3, 4, 5, 6, 7, 8 because these are the group numbers as per the Mendeleev's periodic table. Okay. As per the Mendeleev's periodic table. As per the modern periodic table, their group numbers are 13, 14, 15, 16, 17, 18. Now, if you see here, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically, if you remove 10, right, the number you will be getting is this from each case. And that 10 represents, like basically that 10 is because of this part. Okay. Now, if you see here, group 3, 4, 5, okay, this or this is representing the valence electrons present in these groups. So here the group numbers are in the nutshell. It is representing the number of valence electrons. So once you know the valence electrons, I think it will be easy for you to identify the valency. Right? So if the valence electron is 5, the valency will be 3, H minus 5. And basically it will be gain of electrons. So what happens is, when you have valence electrons, which are 1, 2, 4, right? Then the element has a tendency to lose electrons. When the valence electrons are 4 to 8, then the element is having a tendency to gain electrons. Now 4 is a common number. It means it can be both lost or gained or shared. This number 4. Any element which is having 4 electrons in its valence shell will have a tendency to either lose those 4 electrons or to gain those 4 or to share those 4. Right? Now, since you know that noble gases have a complete octet, so it means their valence electrons are 8. And since the valence electrons are 8, the valency will be 0. Got it, everyone? Yeah. Okay then. So now let's move to the next part of this work, this chapter, and that is the variation in the atomic size. Dekho. Atomic size can also be represented or can also be categorized as radii. Atomic size or atomic radii. Why? That's because an atom is a sphere. It is not circular. No, it's a 3D picture. So an atom is always a sphere, right? Now, when you talk about this atom, which is a sphere, so there's a nucleus and there's a valence shell in which the electrons are lying. So atomic radii or atomic size is defined as the distance from the center of the nucleus to the valence shell of an atom. From the nucleus to the valence shell, whatever is the distance, that will become your atomic radii. Right? Now, we really need to understand that how does this atomic size vary? Achha, one more thing from here. Like if I talk about, we discussed about how the valency variates in a group. What about a period? So in a period, it first increases, as you can see here, +1, then +2, then +3, then +4. It first increases and then it keeps on decreasing. So it first increases, then it decreases along the period. Whereas along a group, it remains constant. Whereas if you talk about these elements, the ones which are lying in between, that is your D block elements, remember? We discussed this in yesterday's class. So these are known as transition metals that we discussed. And the reason why they are known as transition metal is because they show number of valencies. They show multiple valencies. A very common example is iron. Remember, iron makes FeO and Fe2O3. So iron can be present in +2 state or +3 state. So there are two valencies possible. Same way for copper, you might have done +1, +2, and many other elements. So it is because of that, since it has a tendency to show multiple valencies, a number of valencies, that is why we have not considered it. And they are known as transition elements, right? So now let's talk about how the atomic size varies in a periodic table. So when you talk about along the period, so along the period, the atomic size decreases. Okay, the atomic size decreases. The reason is that's because effective nuclear charge increases by 1 unit, and it pulls the valence electrons even closer to the nucleus. Pulls the electron closer to the nucleus. Whereas if I talk about down the group, then the atomic radius increases. That's because new shells are added. Okay, so let's see, let's understand it how, or what is happening actually. See, for instance, for a group, again, I'll be taking the same case and let's take a period case here. Okay. Suppose for group, I'll be taking the same lithium case. So 2, 1, below lithium lies sodium. Its electronic configuration is 281. Below sodium lies potassium. Its electronic configuration is 2881. Right. Now, in all the cases, we have a nucleus. Right. Now, I'll just draw shells. So lithium has how many shells? 2 shells. And you remember shell number represents your period number. So it's going to have 2 shells, right? Now if we talk about sodium, so this is your first shell. This is the second shell. And this is your third shell. There are 3 shells total. KLM. Right. Now here, KLMN. So your first shell, your second shell, your third shell, and then there will be a fourth shell too. So can you see the size part? Of course, the size will keep on decreasing as you add a new shell to it, right? As you add a new shell. Now, you already know that atomic size means the distance from the center of the nucleus to the valence shell. So you can see that this distance is increasing. So down the group, size increases. I think we're pretty clear on this. Now let's talk about period. So for that, let's take 2 examples. Let's take lithium and beryllium. Let's take one more, boron. Now what is happening? The number of shells remains the same, right? They all have 2 shells. They all have two shells. Now, what is the difference? The difference is that they have more number of electrons and more number of protons. Right? That is the difference. They have more number of electrons and protons. Now, what happens? There is a term which we have used, and that is your effective nuclear charge. Now, what do you mean by this term called effective nuclear charge? See, we simply mean that if you add more, if you keep on adding more protons in the nucleus, then what happens? This nucleus, okay, the nucleus, after having more protons, okay, as the protons increases, its attractive power will increase. Yes or no? As the number of protons increases, the attractive power of the nucleus will also increase, right? Right? So as a result, what will happen? Suppose this is your nucleus, right? Mhm. All right, so I'll take this part. Suppose this is your, oh, okay. Okay. Suppose, can you see this? All right. Suppose this is the nucleus, okay? And can you see this part? This is an electron. This is an electron. If it is not visible, then I'll take my ring off, I think. I think now it's visible, okay? So basically, this is this is a nucleus and this is an electron. Previously, they were both standing here. Here, this was the distance. Now, as the number of protons increases, what is happening? Its attractive power is increasing. Now, since its attractive power is increasing, what will happen? It will attract this more towards itself. So this was the nucleus. Previously, this was the location of the electron and the nucleus. Now, the moment nucleus is having more attractive power, the electron will move a little closer to it. The moment it will move a little closer to it, basically the electron alone cannot move. So it will take the space in which it is moving. So the entire shell is a little stretched, or it's a bit attracted towards the nucleus. So since it is attracted towards the nucleus, the distance will decrease. The distance will decrease. Now, whose distance will decrease? The distance between the outermost electron and the nucleus. And it is this that we known as, or which is known as effective nuclear charge, represented by Z effective. So basically, it is because of this sort of attraction that effective nuclear charge increases, and it is because of that the outermost shell comes closer to the nucleus, and thus the size decreases. Right? Make sense? Yes? Oh, wonderful. Now, we talk about the next thing, and that is the variation of metallic and the non-metallic properties. So this appears to be very easy, isn't it? The variation of metallic and non-metallic. So we know that if I look at my periodic table, so there is a staircase like part. So we have seen that basically in our previous class we discussed that it is the staircase which is representing your metalloids. Everything lying to the right hand side will be non-metallic and the left side will be metallic. So basically it is the metalloid which will give us segregation or which will act as a barrier or as a lining between metals and non-metals. Right? It acts as a barrier between that. So variation of metallic and non-metallic properties, how is that happening? See, as we are well aware, if this is the part representing non-metals, if towards the right it means non-metals, so can I say while I'll move from left to right, I have more chances to find out the non-metal? Right? Like I'm moving towards non-metal. So of course my non-metallic character will increase. If I move from left to right or along the period, then I have more chances or I'm moving towards non-metal. So my non-metallic character will increase. Whereas if I move opposite, my metallic character will increase. Right? Same way, if I move down the group, then the metallic character increases. Whereas going down the group, the non-metallic character decreases. So let's understand the reason why. See, when we talk about the metallic character, so how do you classify metallic character in anything? So your metallic character is basically the, like metals are what? Metals are electropositive, right? So metallic character would mean the tendency of an element to lose electron, because only after losing an electron can an element become positively charged or cationic in nature, right? So how easily can an element lose the electron? That will give me its, or that will talk about its electropositive nature, thereby making it a strong metal, right? Now, what is happening? As you move along the period, right? So along the period, when I move, the number of valence electrons increases, right? Now, if the number of valence electrons are increasing, then what? It becomes difficult to remove the electrons. Or what will happen to valency? The valency would be more towards gaining of the electron than to lose the electron. So it becomes difficult to lose electrons. And that is why metallic character decreases. That is why metallic character decreases. Right? Whereas if you talk down the group, while you move down the group, then what happens? Your number of shells are increasing, right? And valence electrons remain same. Thus, it means that, see, if I talk about lithium, sodium, and potassium. Now, see again. In case of lithium, this electron is here. This electron is here. In case of sodium, the electron is here. In case of potassium, the electron is here. Now, in which of the cases do you feel that this electron will face least attraction with the nucleus? When the electron is here or when the electron is here, or when the electron is here. When will it face the least attractions? Right. When it is the farthest from the nucleus, this will face least attraction with nucleus since it is farthest. Agreed? So when you talk about down the group, the number of shells are increasing. Okay. And the valence electrons remains the same. So thus, the outermost electron will face least attraction towards the nucleus since it is farthest. Since it is farthest. Right? And as a result, it will become easily to knock off that electron. Right? It becomes easy to remove that electron. Isn't it? Now, if the electron is removed easily, it means it will lead to a positively charged ion, that is a cation. And cations can only be formed by metals. It means that they are acting as better metals. And this is what we say as the metallic character increases. And vice versa for non-metallic character. So I hope you can write it all by yourself. Same thing in the opposite fashion. And your work is done. Make sense? Yes or no? Yeah? Great. So that's the next thing. And now let's move to the next part, which is the variation of the electronegativity. The variation of electronegativity. So in the metallic character, we just talked about that metals are electropositive, which means your non-metals are electronegative in nature. Electronegative means that they have a tendency to gain electrons. Right? They have a tendency to gain electrons or the tendency to pull electrons in the valence shell. Okay. So basically, electronegativity is the tendency of an element to attract the, like an actual definition would be to attract the shared pair of electrons. But for simplicity's sake, we can just understand it that electronegativity simply means the tendency to pull the electrons towards itself. Okay. So pulling the electrons can be similar, or it is similar to that of the gaining electrons. Pulling the electrons towards itself, similar is to gain the electrons. There's a slight difference that we'll be discussing in the next chapter. What is the difference between electronegativity and there's another thing called electron gain enthalpy. So these are the two things we'll be discussing about. So, so along the period, basically what happens, the electronegativity increases because what is happening? Non-metals are increasing along the period. So what is the tendency of a non-metal? To pull the electrons, to gain the electrons, right? So as a result, the electronegativity increases along the period, whereas it decreases down the group. It decreases down the group and increases along the period. As simple as that. Because of the non-metallic character, you can directly relate it to the non-metallic character. As the non-metallic character increases, electronegativity increases. So this is the trend which is given, right? Because your non-metals have a high tendency to pull the electrons or to gain electron. उसको कितना ही चाहिए? It just needs one electron. So yes, it has a higher tendency to pull the electrons all by itself. So this increases along the period. All right. Make sense? Yeah. Okay. Now we move to another quest, and that is about the atomic size. Now here we are going to discuss a few more additional stuffs in the atomic size. Now what do you mean by the term atomic size? Now the distance between the two nuclei will give me the diameter of an atom. Now see, whenever two atoms are combining, okay, whenever two atoms are combining, so there are varied ways by which they combine. Now, you have done covalent bonding in your last chapter, carbon and its compounds, right? So covalent bonding means when the two atoms are coming close by sharing the electrons, right? For instance, if there is one hydrogen having one outermost electron, another hydrogen having one electron. So now they're sharing their one electron each. And then a bond is formed. So this is your covalent bond. And since a single bond has been formed, so this is your single covalent bond. This is a single covalent bond in which the duplet of each hydrogen is complete, right? So how you pick, like when you are drawing its pictorial representation, so there is one hydrogen atom with its nucleus, there is another hydrogen atom with its nucleus, they are combining together, okay, and this is how we combine them. This is your combination. Now if this is how they're combining, so the distance between the two nuclei is going to give you the diameter of an atom. The distance between the two nuclei will give me the diameter of the atom. So how to give you the bond, how to give you this diameter will represent bond length of a molecule. Now if I divide it by half, so that will give me the radius of that atom. So suppose when the two hydrogens combine, let's say that distance was the distance was 5 picometer. Okay, picometer is just a unit, or just 10 to the power minus 12 meters. So suppose the distance was 5 picometers. So what will be the radius? If the distance between the two hydrogen atoms is 5, what will be the radius of the hydrogen? So radius is exactly half of the total distance. So the radius will be just 2.5. This is what we mean by, or this is how we calculate the covalent bond length. Okay. There are many other kinds of bonds that we have. Okay. So we have metallic bonds, and van der Waals radii. Okay. Along with ionic radii or ionic size. So we will be discussing about that part also in a while. So let's first talk about the metallic bond. Now, technically, two metals never form a bond with one another. So what do we have exactly is a electron C model. We just have a model by which, because of which we just try to uh, understand how the attractions are happening in between the two atoms of a metal. How the attractions are happening. So how does an electron C model looks like? See, when you talk about the atoms which are present in a metal, so they have a tendency to easily lose an electron, right? They can easily lose an electron, right? You just have one electron or two electrons, so they can easily lose the electron. So when you talk about if you want to lose electron, so will you lose if you are holding something? Suppose you are holding your phone. So will you just lose your phone just like that? If someone comes and says, "Give me your phone," and you'll be like, "Lay," you won't do that, right? The person has to fight with you, okay, or like push you hard, okay, or just snatch the phone away. So that person has to apply some force on you to get the phone, isn't it? That person has to apply some force. The same way, even if you have the metals, they have the electron. So what happens? They won't lose the electrons just like that. You need to apply some force, some energy, right? Now that energy is available. Okay, that energy is there. So that energy is even present at your room temperature by the sunlight and the other cases. So what happens? These metals have these atoms. Okay, and there are these electrons of that metal, which is what they are not given out completely. Okay, so they lie in the vicinity of that atom, but they're not exactly the part of it. How can you understand it? So you can understand it in the way in which way would I say? Okay, let's take that example. So do you have a sibling at your house? A smaller child, very, very small child, okay? The person who crawls, that sort of child. Okay. So what actually happens is when you talk about that child, suppose the door is open. Okay, suppose the door is open. Now what do? You know, okay, what will happen when you talk about that small child? Okay, so that small child will, you know, that small child roams around the entire house, है ना? जो छोटे छोटे बच्चे होते हैं उनको तो वैसे ही बहुत आदत होती है कभी यहाँ जाना है कभी वहां जाना है ऐसे घूमने वैसे घूमने राइट सो दैट चाइल्ड इज गोइंग अराउंड ओके इट इज द पार्ट ऑफ द हाउस इन विच इट इज मिसिंग अराउंड नाउ अभी क्या था अभी दैट चाइल्ड वाज इन वन बेडरूम so the child was a part of that bedroom or he or she was not supposed to leave the room ठीक है but the moment the parents are gone the moment the parents are gone अब इस चाइल्ड को क्या लगा मैं तो राजा now I can roam here and there wherever I like it right but does that mean the child can leave the house no the house is locked so the child can indeed roam around okay the child can indeed roam around but the child is not confined to the room but the child is confined to the house right now it is this house which is the atom The child is electron, and the room was the outermost shell. So the child has left that outermost shell, but it has not left the atom completely. Can you imagine it? You have left your room, but you have not left the house. Right? So now you're free to move around, but you're not free to move to go out of the house. Right? So this was the scenario. Okay. So now what will happen is this entire picture can be represented this way, that this is your atom and this is the free electron. So this atom, when it has lost the electron, so when this room has lost the child, it will become positive कि चलो बला टली है ना, and this electron is free to move around the entire house. So this is what you call as the positive charge kernel. And this is the pool of electron, in which, like, this is the pool of electron, or the seal of electron. And it is because of this reason that the entire structure or this way is known as the electron sea model. This is known as the electron sea model. Okay. All right. Is this part clear? Okay. Now here, if you talk about the bonds, are basically attract कौन कर रहा है? So there are strong electrostatic forces of attraction here. But if I talk about the metallic bond length, तो वो क्या होगा? This is one metal, this is one metal atom. This is the distance, and exactly half of this distance is known as your metallic bond. That is your metallic bond. Okay. Now there's another case which is your van der Waals radii. Van der Waals radii only works for noble gases. Okay, it works for noble gases. Up noble gases, you know that whenever you have gases, gases have least force of attraction. Yeah, so the atoms just randomly diffuse here and there. And since it is gas, gaseous atoms, so वैसे भी बहुत they are far apart, right? Now there would be less force of attraction, but doesn't mean there is no force of attraction, right? There is force of attraction, though very minimal. Now, in these atoms, if you talk, the distance between the center of their nuclei, center of the nucleus, that is that distance is your diameter, and half of that distance will become radius. Exactly half of that distance will become your radius. So that will give me the radius of the, it will give me the radius of the noble gas. This will give me the radius of the noble gas. So now if you check your internets, right? What we have done is that this is what I'm going to tell you now. This part, this entire thing is only for Olympiads. Okay, for your NTSC examinations or NSOs, this is not for your boards. ये boards में उतना deep level कोई नहीं पूछता. Okay, this entire thing is for your Olympiads. Now, what happens is, if you talk about, and this thing which I'm going to tell you now, atomic radius we just did increases along the period, decreases along the period and increases down the road, right? But there's a twist in the tail. There's a slight twist, and that twist is only for like higher understanding. And Olympiads. Now, why for only? See, what happens is you might realize with time that generally people keep chemistry with exceptions, which is not true. It's not true. There are no exceptions in chemistry. The only thing is that we are not strong enough to understand the deeper roots of the reasons. ठीक है, बहुत सारी ऐसी चीजें हैं like which are having strong depth knowledge is required, but we have not opened our mind in that direction yet. So it is because of that reason we don't consider it. Okay. Now, what is the twist? The twist is very simple, that along the period, yes, the size decreases. Okay. So that is from group 1 to group 17. But the moment you move from group 17 to 18, what happens? Suddenly the size increases. And why is it increasing? Because of this van der Waals radii. Now, if you will compare the sizes, you remember there was this what we did in the atomic radii part, the covalent radius, right? Now, see here, if I compare with respect to the lengths, this is the length or this is the radius which I'll get in case of covalent. This is the radius which I'll get in the case of, like, see the size of the atom. If I'll make the same size of the atom, right? So this becomes the radius. And if I talk here, again, I have not made the same size. I'm sorry. Because see, there's a very simple logic which works, and that logic is whenever you are doing the comparison, please always compare on the same grounds. You cannot compare someone's beauty with someone's intelligence. You cannot compare someone's handwriting with someone's explanation. You cannot compare any two odd things, volume with mass. That is not the right comparison. You cannot compare distance with volume or speed. So you can get one another from one thing, like in speed and distance with that. That is, you cannot compare the two things together. Okay. So basically, if you are comparing things, you have to compare it on the same grounds. And that is why I've kept the sizes almost of the similar level for each and every atom. So now if you'll see, if this is A size, this is B, this is C. So you will see that A size is the smallest, followed by B, followed by C. It means the size of the covalent radius or the covalent atom. So covalent radius will be the smallest, okay, as compared to the metallic radius, which will be further lesser as compared to the van der Waals radius. Right. So they all are atomic sizes, but then because of the different types of bonding or attractions, their sizes will also have a variating effect. Right? Is this part clear? See guys, since this is Olympiad's level, if you anytime, anywhere feel that you have not able to understand it properly, you can always ask for the DRS. Okay, so that we can sit together and have a proper live interaction. All right. Sure. And now let's move to the ionic size. Now, ionic radius is what? The radius of an ion, right? And ion means cation or an ion, right? The size of the cation or the size of the anion is represented as the ionic radius. So this will be the distance between the nucleus of an ion and the outermost shell of the ion, right? That will give you the ionic size. Okay. Now in this, we have a very important thing that when you talk about your cations, okay, suppose I'll take an example. Okay. Let's take Na plus, let's take neon, and let's take fluoride. Okay. Now, in which neon is neutral, Na plus is a cation, and F negative is an anion. If you'll see the number of protons in each case, right? The number of protons in each case. Now, sodium ion is having 11 protons, neon is having 10, fluoride is having 9, because that is their atomic numbers. Now, if you talk about the electrons in each case, sodium plus is having 1 electron lesser than the neutral state, that is 10. Neon, since it's neutral, so it will have the same number of protons and electrons. And F negative, since it is an anion, it will have 1 extra electron as compared to the number of protons. Now, all these 3 elements have the same number of electrons. Now, those ions or species which are having same number of electrons are known as isoelectronic species. The species having same number of electrons are known as isoelectronic species. Okay, they're isoelectronic. Now see, in Na plus, there are more protons as compared to electrons. So protons if are more, so basically we just have a discussion. If protons are more, they will have greater nuclear attraction, more attraction. So if these are the electrons and these are the protons, so this electron will be more attracted. And if it is attracted more, it will come closer, right? It will come closer. Now, since it will come closer, what can I say? Can I say the size will decrease as compared to the regular sodium? In comparison to regular sodium, the size will be lesser, right? Now, neon is as it is, like it will have the same number of protons and electrons. Now, for fluoride, what will happen? Now, since the electrons are more, so more repulsions will be there. More electrons would mean more repulsions. Now, if the repulsions are more, so what happens? Repulsions are more, matlab size. The electrons will move away from the nucleus because of repulsions, right? If they move away, so their size increases. Now, if I take neon being the neutral species, if agar uski ek general attraction and repulsions hai, so it has similar sorts of attractions and repulsions. Sodium में क्या है? There are more attractions. Fluoride में क्या है? More repulsions. Right. So wherever there is more attraction, that size will be smallest. followed by when the attractions and repulsions are almost similar, right? Followed by the case where there are more repulsions. So repulsions will make the electrons move away from the nucleus. And if they go away from the nucleus, what will happen? The size will increase. So this is your simple order of atomic size. Okay, in case of ions or in case of isoelectronic species, right? So this is the explanation of the thing that why this particular order which I have given is the correct order. What is the reason behind this order? Now what we are going to do is we are going to understand a simple trick here. A very simple trick. Now, if you talk about the isoelectronic species, the trick is very simple, that the radius of isoelectronic species or the size of the isoelectronic species is inversely proportional to their atomic number. The size of the atomic radii of the isoelectronic species is inversely proportional to the atomic number. So if you'll see here, atomic number of fluorine was 9, this is 10, this is 11. So size is inversely proportional. Fluorine was having the smallest atomic number, but the highest size. But this trick is only valid for isoelectronic species, and this will reduce your effort a lot. Will reduce your effort. So it's a very simple, plain trick. Majorly, these kind of questions are asked in Olympiads or your like NTSC examinations. Okay. Clear? In case you still feel that you have any problem in understanding the higher grade stuff, please let me know. Feel free to ask for a DRS or anything. Okay. All right. So that finishes off the basic theory of this chapter, like of this today's topics. Now, in the next topic, we'll be discussing more about other trends and other properties like electron gain enthalpy, electron affinity, etc. So before we talk about that, let's have some quick questions today. The first question is, which of the following statements is not a correct statement about the trends when going from left to right across the period? So the elements become less metallic in nature if you go across the period. So do the elements become less metallic? Yes, they become more non-metallic, so they become less metallic. The number of valence electrons increases. That's again right. As you go along the period, okay, or across the period, the number of valence electrons keeps on increasing. Not the valency, the number of valence electrons, right? Because the atomic number increases, so the number of electrons increases. And the number of shells remains the same. See, the atoms lose their electrons more easily. No. Since I'm moving towards non-metallic character, how can they lose electrons easily? They can gain electrons more easily, right? So that would become your correct answer. Make sense? Yeah. So now let's move to the next question. So the next question says, element X forms a chloride with the formula XCl2, which is a solid with a high melting point. First of all, it's a solid and the melting point is also high. X would most likely be in the same group of the periodic table as, so that element X would belong to which group? Now, since if you talk about the formula, so chlorine's valency, you know, is 1. Okay, let's say the valency of the element X is let's say it's Z. So the formula would become what? XClZ. If I compare it with the compound which is already given, so on comparison, can I say that Z is equal to 2? Or the valency of the element X is 2. Now, if the valency is 2, then the number of valence electrons are also 2. And the number of valence electrons being 2 are found in group 2 elements. So, magnesium is one of those group 2 elements. Right? Make sense? Great. All right. So, guys, that is all for today's session. It was wonderful teaching you for today. Okay, just be prepared for some, again, higher stuff for the next class, which is about electron affinity, ionization enthalpy, etc. So keep connected, keep posted, and that's all for today. We'll meet again in our next class. This is me, Bhavya, signing off for today. Bye.